Now that we're comfortable with dot product, we're going to be using it to determine the scalar form of a plane. And so you've probably learned that a plane can be determined by 3 points. Similarly, when we're dealing with vectors, a plane can be determined by a perpendicular vector and any point on the plane. And so just to see how that looks in 3D, here's my point on the plane, and as you can see, I have a perpendicular vector. That's all I need to determine a plane. If I change the perpendicular vector, you can see I can change the orientation of the plane, and I can change the point anywhere I like. And so if I'm given a perpendicular vector, such as u, and any point on the plane, one thing that will always be true is that that vector u will be perpendicular to any vector that might lie on the plane. And so here's my point on the plane, and now I've created a generalized point, x, y, z, and this vector will always be perpendicular to this defining vector. So as you can see, starting at my point on the plane and going out to x, y, z, this vector is always going to be perpendicular to the defining perpendicular vector. Now I can use my dot product to actually determine the scalar equation of the plane. And so where u is my defining perpendicular vector, and I have the point 1, 4, 5, the generalized vector is found this way: x minus 1, y minus 4, z minus 5. And I can exploit the dot product just by knowing that those two vectors are going to be perpendicular and the dot product is going to be 0. And so when I expand this expression, I'm going to end up with the scalar version of the equation of a plane. And so when I get done, there it is. There's my scalar equation of the plane, and I can use this equation to determine any points I like anywhere on that plane.